Okay, welcome to note set number 40. This is the last video lecture in this series. We've come a long way. We've seen a lot of things, and what we're going to finish off with here is doing for continuous time systems using Laplace transforms the same kind of thing we did recently with discrete time systems, which was handling systems that have initial conditions. So here we're going to be solving differential equations with initial conditions. So these mimic the slides that you've already seen for discrete time, and all the stuff that we've done so far for our analysis of a continuous time system is we've assumed that our inputs could exist for all time. They didn't have to, but they could. And if they did, it's really hard to define what initial conditions would be. And even if our inputs didn't exist for all time, we still assured that they did not have initial conditions. We were not interested in analyzing that case. And as we've said, that's a common view in signal processing and communications. For those kinds of systems, you don't normally even fuss about initial conditions. For that we used, for the analysis there, we used the bilateral Laplace transform, and the key idea was to find the output. All we had to do was worry about this product and take the inverse Laplace transform, and we would get the output. But same thing as in discrete time case, sometimes you want to analyze things in areas like control systems where you've got a system and it's already doing something at the time when you first start applying your control signal to it. And so the thing that it's already doing would be considered to be the initial conditions of the system when you apply your control input to it. And unlike discrete time systems where we had as our initial conditions some number of previous output sample values, for a continuous time system, the initial conditions are considered to be non-zero derivatives at time equal to 0. So you'd have the output at time equal to 0, its first derivative at time equal to 0, maybe its second derivative at time equal to 0, and so on and so forth. And so just like with discrete time, whatever the order of your system is, you need to have that many initial conditions. So to handle this, just like we switched to the one-sided Z transform for discrete time, we're going to switch to the one-sided Laplace transform for continuous time. So the key here is that we are starting from 0 rather than starting our integration from minus infinity. By switching to this one-sided Laplace transform, it will allow us, the mathematical machinery that's available for this allows us to address the initial conditions. So when we switch to the unilateral Laplace transform, most of the properties remain the same, but there's a couple that we have to worry about. And the main one is time differentiation. Remember, we're going to be applying this Laplace transform to the differential equation, and now assuming that the differential equation has some initial conditions. The result is the derivative, the first derivative of x, transforms into still s times x of s, but we now have to account for the derivatives or the initial conditions. So for first order derivative, we need just one initial condition, which is the value of the signal at 0 minus. And that 0 minus part is used to handle the case where x may be discontinuous. If it's discontinuous, we have to use the 0 minus part, which means the limit coming in from the left. So for example, if I have a signal that looks like this and then it jumps discontinuously, the limit from the left is 0 and the limit from the right is this value, say 1. So we would use the value from the left. Now, if it is continuous, then there's no distinction between 0 and 0 minus. So we can always just put 0 minus there to be on the safe side. For the second order derivative, it transforms into s squared times x of s. That's what we had for the bilateral case without any initial conditions. But now we see that we've got two initial conditions coming in. The initial value plus the initial derivative. You can see that when we have a second order system, we'll have a second order derivative, and we will end up with two initial conditions as being required. And in the general case, the nth order derivative, we have Sn times x of s, and then we have this sequence of terms, and you can kind of see what the structure is. So it's no derivative, power of n minus 1, one derivative, power of n minus 2, n minus 2 derivatives, power of s, n minus 1 derivatives, power of 0. And so the key is that the number of derivatives and the power of s will always add to be n minus 1. So that's how we figure out all those terms. So let's see how we apply this to a first order differential equation. So here's our differential equation, and we're going to apply the Laplace transform to both sides. And when we do that, we have by linearity, we pass the Laplace transform through, and it snuggles up around that, and it snuggles up around that, and it snuggles up around that. So here and here, pretty straightforward. We get a times y of s, b times x of s, and now for the derivative term, we have to use the property for Laplace transform of a derivative. So we do the s times y of s, and then we account for the initial condition. And since this is a first order derivative, we only need one initial condition. And so there is the initial condition on the output of the system. And so now solving that for y of s, we end up with something that looks like this. And so now this tells us what the output looks like in the Laplace domain, and now we have to do an inverse Laplace transform to see what the solution looks like in the time domain. But we can already start making some assessments. We see here that this part of the solution is influenced only by the initial condition. So we say that's the part driven by the initial condition. And then this part is driven by the input, and we notice that if we were to set the input to 0, this term would go away, so we're left with just this term, which is why we call it the zero input solution. And likewise, that term is the part driven by the input, and if we were to set the initial condition to 0, this part would go away, and this is all we would be left with. And so we use the term state to represent initial condition, and so this part is called the zero state solution. So just like discrete time, we break our solution down into these two parts. Zero input solution, which is driven by the initial condition. Zero state solution, which is driven by the input. And one thing that we note here is that we see s plus a show up in both places. If we go up here and think about what the transfer function of this thing is going to look like, the transfer function h of s for this thing is going to end up being b over s plus a, and we see that that is the transfer function right there. And not only that, but it's also what's known as the characteristic polynomial of the system. So the characteristic polynomial shows up in the denominator of the transfer function, and it also shows up in the denominator of the zero input solution. So that's key insight. Same big idea that we saw for discrete time. So let's take a specific example here, our old friend the RC circuit, but now we're going to hit it with a unit step. So there's the differential equation that we have for the RC circuit. Here's our RC time constant. And now we have the initial condition showing up there, and we see the transfer function showing up here, and again we see how the name transfer function arises, because what it does is it's the part that transfers the contribution of the input into the output. So it's a very nicely chosen name. So now for this particular example, we've been told that the input is a unit step, and you should know how this RC circuit behaves in the presence of that input, but it's always good doing an example where you kind of know what the answer is going to look like. So we look at our Laplace transform table, and we find that a unit step transforms over into 1 over s, and so now that's going to go in up here. And so now we end up having our total Laplace transform of the output looking like this, and it's just a function of s. Well, you might say, well, but there's some other things in there. Well, yeah, but those are fixed parameters. S is a variable, and so now we need to apply the inverse Laplace transform to this. And so we apply the inverse Laplace transform to both sides. I guess this should be ILT. And when we do that, we have something that looks like that. Now we need to find the inverse Laplace transform of that. And so the result for this first term here is the zero input solution, and it's pretty straightforward. You look that up; it's on your table. So you just look it up, and so there it is. That's the part that is the zero input solution part, and that would look like that. So here, if we assume that our initial condition is positive, we know that what that means is, for this circuit, that means that the capacitor was initially charged to that value. And if there were no input on this circuit, we would be just simply discharging this capacitor back through that resistor. And we know that that decays like that. But now to look at the other part, we need to break that apart into these two different parts. And we can do that formally with partial fraction expansion, but in this case it's pretty straightforward to see that that is the case. And you've already done partial fraction expansions, so we don't have to dwell on that. So we end up passing the inverse Laplace transform through each of these two terms. So we get the inverse Laplace transform of 1 over s, and then the inverse Laplace transform of something that looks like that. And again, both of these are on our table, so we can easily look those things up. Inverse Laplace transform of 1 over s is u of t. Inverse Laplace transform of this is the decaying exponential. And so if we combine those two things together, we can write it in this form. And so now that's also something that you know. If this RC circuit is has zero initial conditions and we apply a unit step to this, you know what that thing's going to look like. And there it is, charging up to the applied voltage of 1. You've seen that in your circuits class, so you should be extremely familiar with that. And so if we put all these things together, we have the zero state part that comes from the input, and we have the zero input part that comes from the initial conditions, and we add all those together. Now, yes, it is possible to notice that we have a common term, and we can combine those. And if all you're interested in is the final answer, then that's a perfect way to end up expressing it. But by keeping them separate, we can keep track of what part of our system affects what, so that when your manager comes along and says, oh, you know what, I gave you the wrong information. That initial condition that I told you is not correct. I just heard from our field team that the initial conditions are going to be different. You don't have to go back and untangle your whole solution. You can just go in and say, all I have to do is change that part. And plus it just gives a lot more insight into how the system actually works. Now what we see for this is that the initial condition part decays away, but the input part persists. And in fact, if we go back and look at before we even combine these two things together, we should see that there are two parts to the input driven part. One is a transient that will decay away, and it decays away because it has the same behavior as the denominator of the initial condition part, right? So the initial condition part decays away, and this part also decays away. So we call this the transient part of the zero state solution, and this is the steady state part of the solution. It kind of tells us that once things settle down, what is the system really going to be doing? It's going to be behaving like this. This transient part combines with this initially, but eventually this decays away, and we know that that's how it's going to behave in the long run. So here's those different parts. So this is the zero input response decaying away. Here is the zero state response, both parts charging up to 1. Now in this example I've chosen the initial voltage on the capacitor to be 5, so that part starts at 5 and decays down. This part starts at 0 and decays, reverse decays up to 1, and when you combine them together you get this. It starts at 5 because this was 5 and this was 0, and then ultimately this goes to 0 and this goes to 1. So we see that this decays from 5 down to 1. That's our total response. So that's a nice insight. And now we can look at a circuit with two energy storing devices, and we get a second order differential equation. Now we're going to need two initial conditions. We'll assume that our input is causal. And so now because of this assumption, when we do our derivatives, we won't have any of the initial condition terms showing up. We have these initial conditions. They show up here on the left side when we do the Laplace transform, but on the right side we're assuming a causal input so that x of 0 minus is 0. So we don't get any of those terms like that over there. And so those just come from the derivative properties for accounting for the initial conditions. Then we solve for y of s, and again the big ideas that we see, two different parts. This is all driven by initial conditions. This is all driven by input. And another big thing that we see here is that both of them are over the same characteristic. I say characteristic equation, really should be characteristic polynomial. So that characteristic polynomial comes into play here. It just pops up and it shows up in both places. It happened for the first order case. It happens for all orders. So it's not just a fluke. It happens all the time. So like before, we need to transform this back into the time domain if we want to see how this thing is going to behave. So to get a feel for this, let's just look at the zero input solution. So just this part, just to get a feeling for this. I've just grouped it. We have an S term and we have a constant term. So we would have to do some sort of analysis of this to determine how to get it from our table. And if we look on our table, we've got two very helpful Laplace transform pairs that are helpful for second order systems. And the one that we want is this one. since we have an s plus a constant. So that's what we have. So all we have to really do is match up all the values here, the alphas, the zetas, the omega sub n's, with the things that we have up there, and apply this. So when we do that, what we get is something like this. Now, notice that if we didn't have if our y of 0 minus was equal to 0, we would lose that s term, and we'd have to use the other one of these two. So anyway, each of those is available, and it helps to know that both of those are there. Really, the only distinction is whether we have a phase or not. So the basic behavior is the same regardless. So let's take these as some example initial conditions. If we plug in those values, we get something like this, and I've just pulled this 2 out in front since it shows up in all of those terms. So now let's assume that for our system our A0 is 100 and our A1 is 4. Now we compare what we actually have to the form on the Laplace transform table. And by doing that, we make these identifications. So if we say alpha is equal to 6, beta is equal to 2, omega sub n squared is 100, that means omega sub n is 10, 2 zeta omega sub n is 4, and then if we combine all of that, we end up getting zeta is equal to 0.2. So all of this stuff tells us that we have an underdamped system, and we use all of this stuff. The formula on the table tells us how to compute the A value. So A comes out to be 2.16, tells us how to compute this phi, which comes out to be 1.18 radians. And finally, our solution looks like this. So here's the big picture. We've got a system that's underdamped, and we see that we have decayed oscillatory behavior. So a system that is underdamped, a second order system that is underdamped, will oscillate. A first order system cannot oscillate. So we only get oscillations when we have complex poles in our system. And we get complex poles when we have zeta less than 1 for a particular term. So there's a nice plot of that showing the oscillation, and we can zoom in and check that yes, indeed, the slope there is +4 and the value is 2, so that matches what we've assumed for our initial conditions. If we now think about the nth order case, very similar kind of thing. We just make an assumption here that m is less than n, so that we don't get into there's some persnickety trouble that we are avoiding by doing that. And we look at what happens. We get some polynomial that depends upon the ICs. We get a numerator polynomial that depends on the input side, but then the most important thing is this output side polynomial shows up both here and here. That's the characteristic polynomial that sets the behavior of how the system is going to behave. So if we break this into the different parts like we're used to, we're still going to have a part that's due to the initial conditions and a part that's due to the input. And then we can further expand this thing into a part that still has an A of s at the bottom and still has a dx of s at the bottom. And then these two top parts would be found from like a partial fraction kind of thing. Again, it's not important that you right now see how to find those. What's important is that you recognize that if I have a product of these two things, I can break it into a sum of two terms that have those as individual denominators. And then the important thing is here to see that what we end up with are three different terms. One term is the zero input response due to the being driven by the initial conditions. The other part is the zero state response, which is coming from the effect of the input, but that gets broken into two parts. One has a denominator that is the characteristic polynomial, and for a stable system that will decay, and we call that the transient response. The other part will depend upon the denominator of the input, and its behavior will depend upon what that input denominator looks like. But nonetheless, we call that the steady state response because it's not transiently leaving because of the system's transient behavior. So if all the initial conditions are zero, and we're just looking at the zero state case, we get the part that we've been solving for all along, h of s times x of s. And so the zero state response, even for the part that we've been looking at, can always be broken into this transient response part and this steady state response part. So just summarizing here what we've seen, we can, from the differential equation, easily write the transfer function by inspection. The denominator of that transfer function is the characteristic, I should say polynomial here, of the differential equation, and the roots of that denominator tell us the basic characteristics of the solution, whether it's going to be oscillatory, whether it's going to decay or not, and that comes from the stability or non-stability of the system. So big picture, the roots of the characteristic polynomial drive the nature of the system response, and the Laplace transform really gives us the insight to be able to see that. And there are three parts that contribute to this system's response. The part driven by the initial conditions, and this will decay away if we have roots that are that have negative real parts. So in other words, poles in the left half plane. So a stable system, and we'll see a part that's driven by the input, and that will decay away again due to the poles, and that's called the transient response. And then we'll see a part that's driven solely by the input and has no flavor of the poles of the system, and that part is called the steady state response. So that ends our video lectures. We'll talk about some of this stuff in the classroom, and hopefully you're able to now have much more insight into how these kinds of systems behave. Thanks.